Hi.
Hello, how are you?
Good.
Let's see. Uh, yeah, I'm at on campus right now, so there might be some background noise in the back.
Oh, okay.
Yeah, let me join my the Zoom from the iPad. Let's
Okay.
see. Let's see. Okay, share screen. Yeah, let me make this a co-host. Okay, so do you have any questions so far? That we could go over Diels-Alder reactions.
Um, I was doing Maria Jones practice
Hmm.
worksheet
Yeah.
and I didn't know to do a lot of them.
Oh, right. Can you send me an email of that copy so that I could post it here and we could go over the worksheet together?
Uh,
Yeah, I'll send you my email on the chat.
I can also share oh
Oh yeah,
well,
share screen. Yeah.
oh
Uh
I don't know if you have access to her folder.
yeah, I don't have access to it. So
Okay.
so you can share screen from your iPad or laptop, or you can send the
Yeah.
copy to my email.
Okay.
What worksheet were you doing? Like what practice problems? Like was it the conjugated diene addition with HX or X2 or Diels-Alder reaction?
Oh, I was doing just all kinds.
Oh, alkynes. Okay, okay.
Yeah.
Yeah.
Um, I don't know how to share this. Let me see.
Mhm. Yeah, this week I'm gonna start going back to Pascal's lectures. Last week I couldn't go. I was so busy last week.
Can you, well, I don't know how, wait, can you see it?
Oh, are you sharing your screen?
Yeah.
Let me see. Stop share. I don't see your screen. Are you sharing it from Zoom or
I'm trying to connect my iPad.
oh, connect your iPad.
Well, never mind. I can just share my screen.
Okay, okay.
Uh,
And I think I can annotate on the Zoom if you're sharing it from your computer.
okay.
Oh, I heard that the test results came back. How did you do?
I did really bad.
Oh no. How,
I,
how how is it compared to the average? Like around
uh,
average, below,
just
above,
around it,
around average. I
actually.
see.
Yeah.
Yeah, it's
I
okay.
could have done better.
Yeah, room for improvement. We could go over like your mistakes as well. I think I have the a copy of the key. So
Sure.
if you have any questions on the exam, like what you got wrong, we could go over that as well.
Okay.
Yeah, to review the mistakes and avoid them on the final.
Yeah. So like the first
Mm.
one, the answer was like no reaction. And I thought, and I I don't know why it was that.
Right. So when you see Na, NH2, and ammonia liquid, you know how the Na is always positively charged, and that makes the NH2 always negatively charged?
Yeah.
That NH2 minus is a strong base, where that strong base is going to deprotonate an acidic hydrogen. We said earlier that in a terminal alkyne, there is a hydrogen that is acidic enough for a strong base like NH2 minus to deprotonate. But in this case, we don't have any SPCH bond. The alkyne in this example is internal alkyne. That means that the carbon on both sides of the alkyne has no hydrogens at all.
Oh,
Yeah, there's no hydrogens on both carbons of the alkyne. All the other hydrogens are on an sp3 carbon, which is not acidic enough.
so NaNH2 only reacts with terminal alkynes.
Yeah, NaNH2 only reacts with terminal alkynes that has at least one hydrogen. That's right.
Okay.
Mhm.
And yeah, and I was confused by D too.
Oh, right. So D right here, Pascal in lecture said that he's going to skip over this for now because he's going to return back to it when we get to the last two chapters. But let's just go over this just in case he puts it on the exam. Because
Oh,
because
okay.
even though he said that, I don't trust him. Like he might put it on the exam.
Okay.
uh, Right. So you know how when we have an alkyne anion, remember that chart I made that it could do 5 reactions? Like the first one was acid base, the second one was SN2, the third one was E2, the fourth one was carbonyl, and then the fifth one was epoxide opening. So go back to that like workshop notes or look back at your notes where you find that those 5 reactions.
Wait, in
Right.
alkynes? Alkyne.
Yeah, in the alkyne content review.
Oh,
Right. Whenever we have that alkyne anion here, which is this nucleophile, right? That nucleophile or base can do 5 different reactions. Nucleophile or base. One reaction could be acid base. Another reaction could be SN2, which works on primary halo alkanes or any good leaving group. Other one could is E2, secondary, tertiary halo alkane. The third one is nucleophilic addition to carbonyl. He didn't go over this in lecture, which is this example right here. The last one is epoxide opening, which is 118A. And epoxide opening in basic conditions because we have a negative charge. A negative charge is basic conditions, right? So the reaction here is nucleophilic addition. Well, you know how the negative charge on that alkyne is the nucleophile? Our electrophile in the molecule is this carbonyl carbon right there because that is partial positive. Right? Wait, do you see my annotations on the
yeah,
screen? Okay, okay.
yeah.
That's good. Where is this nucleophile here, the start atom, is going to attack that dot atom right there. And when that happens, we're going to pop the double bond onto that oxygen right there. Right? And then connecting the two molecules together, we get this. Um, this is the dot, which is attached to an O minus. That dot is attached to the star. This is the new bond that we made. That's new right there. And that star is attached to an alkyne, like that. That's part of the alkyne. The star atom is part of the alkyne. Right?
We don't need to know the mechanism, right?
You don't need to know it, but it helps if you do know the mechanism, like what happens on how we get to here,
Okay.
right? Because yeah, right, like
But is that like the
mhm.
whole mechanism? Just the double bond moves to the oxygen and it gives a place for the triple bond?
Yeah, right. Where the first step of the mechanism is that the negative charge carbon on the alkyne attacks the carbonyl carbon. And then when that attacks the carbonyl carbon, the double bond in the carbonyl, which is the carbon double bond oxygen, moves to the oxygen and gives that oxygen a negative charge. Because before it only had 2 lone pairs of electrons, it gained an extra lone pair from the double bond,
Oh, okay.
right? And then we bring in the second step, which that O minus is going to protonate the H3O plus, and that becomes neutral alcohol. Now, what do you think the third step is going to do with the H2 Lindlar's catalyst?
It's cis
Yeah,
alkene.
uh-huh. But in this case, it doesn't really matter because there's
It's
nothing on
same.
the other end.
Yeah.
It's just gonna become an alkene like that. We can't say cis because um there's no group on the other end.
Okay.
So the first reaction, he did not go over in lecture yet. Yet he said he will, but I don't know. He might put on the test.
So
Yeah.
like the five reactions you listed are all for alkyne alkene reactions.
All these five here are for alkynyl anion, which is a negative charge on the alkyne.
Oh, okay.
And there's a chart on it on my content review notes where it looks like this right here, the five arrows like that, and then one, two, three, four, five, and then the five different products here. Right.
Okay.
Where this reaction on part D specifically is reaction four, nucleophilic addition to carbonyl.
Okay.
Yeah. And he did not go over that. Yeah.
Wait.
All he did was he went over the SN2 reaction in lecture. He didn't go over the acid base E2 or epoxide opening. He just went over SN2 in lecture.
I
But
think he finished alkyne reactions in like 20 minutes, so
yeah, yeah. And he just moved on to chapter 14 right away.
yeah.
Yeah.
Oh, and also for the well, oops.
Mhm. Oh, wait, let me screenshot this and so I could post it on the notes so you can review it afterwards. Screenshot. Okay, got it.
Well, I'm also taking notes, so
Yeah, that's good. That's good. Well, were you able to access the notes from our previous office hours as well, like on the school page?
oh, I didn't try to.
Oh, I see, see. Yeah, all the previous office hours that we had, there's recordings on there, and also the notes that I wrote during the office hours. So you could go back and review it if you want to. It's under the classroom module, like the classroom spring 2024 module, in whatever week the office hour was.
Wait, is it on Canvas?
Oh, not on Canvas. It's on
On the
the school
school?
page.
Oh,
Yeah, the
okay,
school
okay.
page.
Got it.
Yeah, the school page. There's different modules. Go to the classroom module, spring 2024, and then all the notes will be there from the previous
Okay,
office hours.
okay, that's cool.
Uh-huh. Yeah.
Um, can I get rid of this?
Yeah, yeah. Let me get rid of that. Okay.
Yeah,
Yeah.
the this one too, the synthesis.
Oh, the synthesis for this one. Yeah, so you know how these are Z-alkenes because
Yeah,
the two highest particles are on the same side?
yeah.
We're trying to create a E-alkene because the two highest particles are on opposite side.
Mm-hmm.
Let's go backwards. Let's say that those double bonds came from a triple bond like that, right?
Do you always assume that alkenes come from alkynes?
Not always because alkenes could also come from E2 reactions like NaOH, NaOET,
Yeah.
um, right? But then it just depends on what the reactant is. In the reactant here, we're trying to come from a Z alkene to an E alkene, where we can make E alkenes or Z alkenes depending on what reagent we use. If we start from an alkyne and we try to make an E alkene, do you remember the set of reagents we have to use to make E or trans alkenes?
Na and
Yeah,
H2.
Na, oh not NaNH2, that's the strong base.
Oh, just the Na radical.
Yeah, Na radical in ammonia liquid. This is different than NaNH2, right? This is not NaNH2. This is
Okay.
Na radical in ammonia NH3 liquid, which will convert all of the alkynes into the alkene. Okay. Now, do you remember how we can make alkynes?
Alkynes.
Uh-huh. Like let's say how do we make double bonds? Like what is one reaction that we can make double bonds?
Uh, are we saying E2 here
Yeah,
or
yeah, E2, that's right.
okay.
Where we could do E2 two times. One time to make the alkene, the second time to make the alkyne.
Oh, okay.
That means we need two good Libby groups for the E2 two times.
Oh, okay.
Um, how can we add bromines on both sides of the alkene?
Br2.
Yep, Br2 and no water, no alcohol. And let's say excess or 2-EQ to react with all of the alkenes. Okay. And then let's say we have NaNH2 strong base to do the E2 reaction, excess as well to do E2 in this case, four times. Two times for this, right? Two times E2 to make the alkyne there. Another two times E2 for that. Right. So this reaction does E2 four times.
Okay.
Mhm.
In what case do we need to write the solvent?
Oh wait. It is you could write the solvent as well, but since this is synthesis, um you don't have to write the solvent. That's just optional. You could if you want to.
Are there like cases that we need to write the solvents, yes or yes?
Uh, if you had like let's say this alkene here, and we're trying to make, let's say, this bromine with an alcohol nearby, we can't just say Br2. The solvent here is H2O, right? In that case, that is important to include because the solvent is reacting in the reaction, which is the OH in the product. In the other cases, if the solvent does not make anything happen in the reaction, like it doesn't do anything in the reaction, then the solvent is optional to write in synthesis. But if the
Okay.
solvent does react, then you have to write it down.
Okay.
Yeah.
Oh, do you
Wait,
need
let
to?
me
Oh,
clear this.
oh, okay.
Okay, there we go.
Um, I just had a question about this. Does it work as Na radical too?
Yeah, yeah. If you see lithium or Na, it does the same exact thing.
Oh, okay.
Uh,
And oh, right. I forgot how can you get
Mm.
from an alkyne
Alkene.
to a aldehyde?
Oh, well, aldehyde, aldehyde.
Yeah.
Okay, okay. So this is synthesis for here. So how many carbons do we have in the reactant?
For
Four. One, two, three, four. How about in the product? How many carbons do we have in the product?
only two.
Yeah, two. So you know how we have less carbons in the product than in the reactants?
Yeah.
What is one reaction you learned that can cut up the molecule?
O3.
Yeah, O3. So let's go backwards and let's say that came from O3, first step, second step, H2S. Let's say that that came from this alkene, right? Because you know how we make cut in the alkene in
Yeah.
half and then we put two oxygens in the middle. That gives us two of these right
Oh,
here,
okay.
right? And it doesn't have to be trans alkene. It could also be a cis alkene because when we make that cut right there, we still get the same answer, right?
Oh, okay.
Still aldehydes. And it doesn't matter if the alkene was E or Z. So in this first reaction here, you could use two different reagents. You could make the cis alkene or the trans alkene.
H2,
H2 with what catalyst? PDC or Lindlar's?
Lindlar.
Yeah, Lindlar's. Why can't you do PDC? Some people might do PDC, but what's the problem with that?
It goes to alkane
Yeah, it
directly.
goes to alkane, and from the alkane we can't do the O3 reaction.
Yeah. Okay, that makes sense.
Mhm. So when you see less carbons on the product, think of a reaction that can cut up things, which there's one reaction you learned, which is the O3 reaction.
Okay.
Uh-huh. So you know how in synthesis it's sometimes helpful to go backwards, like see what could
Yeah.
cut up things, and then from going backwards you could go forwards and then try to meet in the middle.
Yeah.
Mhm.
Yeah, I think. Do you need to take it? Okay.
Yeah.
Um, my last question.
Mhm.
Oh well, it was from. Can you see it?
Yeah, I see it.
Are this like IR
Mm.
for alkynes?
IR for alkynes.
I wasn't sure about this.
Yeah, since this is workshop 6, which is the workshop we just did right on alkynes,
Yeah.
there's probably an alkyne here.
Oh, okay.
Yeah. And we could double check that because if we have an alkyne, how many DOU do we have to have at least?
Two.
Two. So let's make sure that is correct. Wait, 2 times 8 is 16. 16 plus 2 is 18. 18 minus 12 is 6. 6 divided by 2 is 3. So we do have at least two. So there could be an alkyne here. Most likely we do because this is the alkyne worksheet.
Oh, okay.
Yeah. And NMR, so weird.
I don't know. I don't even know if we're gonna get NMR again on the second midterm.
Yeah. On the first midterm, what the NMR problem, did he give you an HNMR? Let me see.
He gave separated.
Oh,
Yeah,
separated from
HMR. Yeah.
HNMR. Oh, and then you had to predict. Oh, so you could make any reasonable structure. Like there's not one correct answer. You could get like different correct answers for this.
I don't know. I actually got like points off, but like I thought it made sense with the.
Oh, I see. I could check that in person, like when you show it to me, like during a content reveal session or something like that.
Sure.
Yeah. Mhm. Yeah.
Yeah, I
Let's
don't know how
see.
you have. I don't know how to look at this.
Oh, for the spectroscopy here. Okay, let me try this from scratch and then show you my thought process.
Okay.
I might get it wrong, but this is how I would do this here, right? Because spectroscopy is my weak spot in OChem, like H&MR. So the first thing I always do is I always calculate the DOU, which we did earlier, which is 3. The next thing I do is I look at the IR and see what functional groups I have. I see that this is the regular 3000 range, so that's gonna be the regular sp3CH bond. This is between the 2100 to 2300, which is the triple bond region. It could either be an alkyne or it could be a nitrile. We do not have any nitrogens in the chemical formula, so we don't have a nitrile. 1700 here is our carbonyl, carbon double bond oxygen. So I know I have a triple bond and a carbonyl. That satisfies the 3 DOU right there. Because triple bond is 2 DOU, carbonyl is 1 DOU. Right.
Okay.
So the next thing I do is look at the HNMR. I don't look at the CNMR. Like I don't know how to read that. Um, I just look at the HNMR. So let's see. I'm gonna guess that this one hydrogen right there that is broad is an alcohol. because you know how alcohol peaks are between 0.5 to 5 ppm range, and they have a broad peak like that, like
Yeah,
no sharp peak. So that's the broadest peak we have, and that's up there. So I'm gonna say that that is an alcohol.
but we didn't get anything that IR.
Oh yeah, yeah, you're right, you're right, you're right, you're right. It's cannot be an alcohol then.
Oh, okay.
Because if that was an alcohol, we need 3,300 around.
Yeah.
Yeah, so no alcohol. I'm gonna guess that hydrogen could be an alkyne hydrogen, maybe terminal alkyne. Then
Are like
say
terminal alkynes also like broad peaks?
um I never heard of that before, but if that's the
Oh,
case, then that's interesting.
I'm not sure.
Yeah, yeah. Let me search it up. Just in case. Are terminal alkyne hydrogens broad on the H NMR? Let's see. Oh, they do have broad signals around 5 to 7.
Oh,
Yes. See, let me see an example. Hmm. Yeah, they say there is a broad peak. Okay, so let's just guess that that is a terminal alkyne. I'm just guessing. Right. Okay. So we see that these three hydrogens here have no neighbors. So, hmm, no neighbors. I could put a carbonyl right there because you know how that carbon there has no hydrogens.
yeah.
So I'm just gonna put that right there. Just a guess. And then we have three hydrogens with hmm, two hydrogens in quartet, three neighbors. Mm, let's
Yeah, that
see,
whole
this is
quartet
weird.
was so weird.
Hmm. That means three neighbors. Let's see. Two hydrogens. It has to have three neighbors. So it could be um mm, something like this maybe, where the two neighbors could be on the right side and the one neighbor could be on the left side. Wait, let me just erase this. Okay. Does the fragment below make sense where the two hydrogens quartet has three neighbors, two neighbors coming from the right side and then one
Yeah,
neighbor coming from the left side? Right. So we also have three hydrogens with one neighbor. So that could be this peak right here, like that, right? Where there's only one neighbor right there. If that's the case, right, I'm gonna say that that CH3 is this CH3 right here. I'm gonna end the chain right there. Does that make sense? Like how I made those three hydrogens that, like these three hydrogens here,
yeah,
it has one neighbor, so that's why it's a doublet. The 2H with the quartet is the 2H in the middle right there,
yeah,
right? And you notice how we have one hydrogen right here. That one hydrogen on that carbon is going to be that one hydrogen right there on the HNMR. And you notice how it's very de-shielded.
mm-hmm.
Since it's very de-shielded, it has to be next to an oxygen like that because it's
Okay,
very de-shielded.
okay.
And also, we have two hydrogens that are also de-shielded. So I'm going to say those two hydrogens that are de-shielded are these two hydrogens right here. Right. So we could cross out that peak, cross out this peak, cross out that peak because we already used that up. Um, And those two hydrogens, they have two neighbors because it's a triplet. So I'm gonna say those two neighbors are these two right here. And what? Okay. So, hmm, okay, I'm stuck.
Okay.
Yeah, can I see the key to this?
Let me
Yeah, if we look at the key, we could try explaining each hydrogen individually.
wait.
Oh my gosh.
Oh
There's
yeah.
an alcohol?
Oh, there was an alcohol.
Okay, so typo. There should be 3,300 feet there.
Okay. Okay.
Yeah, but that wasn't possible.
So like that thing is still the alcohol.
Hmm.
Then where will the carbonyl, well, the alkyne be? Oh, no alkyne.
Yeah, no alkyne hydrogen. It's
Okay,
internal.
yeah. Okay, okay.
Right. Oh my gosh, this IR. Uh-huh. Okay, let's make sense of all the other hydrogens. The three hydrogens with no neighbors are these three hydrogens right here.
Yeah.
The two hydrogens here that is deshielded are these two hydrogens here with two neighbors, which are these two neighbors right here.
Yeah.
These two hydrogens here has three neighbors, which is this quartet right there.
Uh-huh.
These three hydrogens right here with only one neighbor are those three hydrogens right there with one neighbor.
Yeah.
This one hydrogen right here that is very deshielded and with one, two, three, four, five, six, five neighbors is that one hydrogen right there with five neighbors.
Okay.
Right. And then this alcohol H is that alcohol H right there. Nice. And 2-DOU. We got the alkyne and we got the carbonyl. Right. And the IR should also have 3,300 for this alcohol. Yeah.
Good. Okay.
Yeah.
That's hard.
Typo.
Yeah. So like, um, where will the alkyne be on the NMR? Is
The
it from 5 to 7?
the alkyne terminal hydrogen here.
Yeah.
I always thought it was between 2 to 3.
Oh, 2 to 3.
Yeah, 2 to 3. Because you know how that's the alpha region where the hydrogen is alpha to like a alkene, alpha to a carbonyl,
Yeah.
alpha to alkyne. Oh no, that's the alkyne hydrogen. But it could have also been alpha to an alkyne like that. But let me
Oh,
double
okay,
check
okay.
that. Terminal alkyne hydrogen on HNMR. Yeah. It says it shows up between 1.7 to 3.1. So 2 to 3.
Okay.
2 to 3. Yeah. And there's nothing in 2 to 3 here. Yeah.
Oh, so it's just, oh, okay. So it's just like this.
Yeah. The 2 to 3 region right there um shows that alpha hydrogen right here and that alkyne hydrogen right there. Right. And you know how when we count the number of neighbors, we count like one, two, three atoms away, and if it's a hydrogen, it's a neighbor. For terminal alkyne hydrogens, that's not the case. Um, one, two, three. We count this as a neighbor, even though it's four away, because think of that triple bond as very short, right? Short
Okay.
triple bond. So you could just skip over that and say this is like two, and this is three. and that counts as one neighbor, which is a doublet right there. This hydrogen here that's alpha to the alkyne has one, two, three, uh, four, like around four neighbors. But the reason why it's very complicated is because it's coupling with the alkyne hydrogen there. Complex terminal alkyne hydrogen. So you could see like this, even though it has like three neighbors, that should be a quartet like that. But in that quartet, you should see like a doublet in that quartet because of the terminal alkyne there.
Oh, yeah,
Yeah,
okay.
doublet of quartet,
Makes sense.
right? Where the 2 to 3 region is the alpha region or the alkyne, terminal alkyne hydrogen region.
Okay. Yeah, that was it from the worksheet.
Oh, I see.
Uh,
You want to try the other worksheet, like the conjugated diene one, or want to go over the exam questions?
um, we can go over all kind stuff more.
Alkyne stuff?
Yeah.
Okay. Are there any other alkyne
Is
worksheets?
the diethyl, well, the alder thing,
Uh-huh.
the dying stuff from the new chapter?
Yes, chapter 14. That's chapter 14.
Okay, maybe the new stuff too.
Okay, the new stuff.
Yeah.
Mm-hmm. Okay. So let's see. So Diels-Alder reaction has two reactants, a diene and a dienophile. When you put them under heat or light, you always get a cyclohexene. So a diene is going to be basically two alkenes right there that are conjugated. Conjugated meaning that they could do resonance with each other, right? And it has to be in this form right here. This is called the S-cis form, right? It cannot be in the S-trans form, which this is the S-trans form. That would not work with Diels-Alder. Does not work with Diels-Alder. But if we put it under heat, this single bond right here can rotate into the S-cis diene, which will work with Diels-Alder. A dienophile is just one double bond right there, like any double bond. Where this dienophile really likes reacting with diene. If we put that under heat or light, here's the whole mechanism. It's just three arrows. This carbon attacks that carbon right there to make a bond. That carbon attacks that carbon to make a bond. And this double bond here makes a double bond right there. So to keep track of everything, let's number this 1, 2, 3, 4, 5, 6. We're gonna make a six-membered ring, which is this template right here. So that's 1, 2, 3, 4, 5, 6. Let me make them go outside like that. Right. Where there is a double bond between 2 and 3, because that double bond between 2 and 3 came from that double bond between 3 and 4. Right? That's why there's no more double bond between 3 and 4 and no more double bond between 1 and 2. Because that double bond between 1 and 2 made this new bond between 1 and 6. Right? The double bond between 5 and 6 made a bond between 4 and 5, which is why there's no more double bond between 5 and 6. Do these arrows make sense on how that happened?
Yeah, does it
Uh-huh.
just happen because there's heat and light?
Yeah, it just happens because there's heat and light.
Okay.
That's right. Uh-huh. Where in this reaction, right, the diene is going to be our nucleophile. The dienophile is our electrophile. Right? Another way that you could see this is this charge thing right here. If I draw the resonance structure like this, push that double bond there, that double bond goes up here, we get this resonance structure here. Does this make sense how I got that resonance structure?
Yeah.
If I have this diene right here, I could push this diene down there to get this resonance structure here, right? Once I get that resonance structure, I want the charges to align to each other. So I want the negative charge here, positive charge here. I want the negative charge here, positive charge here. These charges are attracted to each other, so they are aligned, where the negative charge attacks that positive charge, negative charge attack positive charge, make the new bond. Well, there's no double bond there. There's only a single bond because when we draw the resonance, one of the double bonds became that lone pair of electrons right there. And when we connect the two pieces, that's what we get right there. Right. We said that the diene was the nucleophile, so that means that the Diels-Alder reaction will be faster if there are EDGs on it. Have you learned about the term EDG and EWG?
Yeah, you went over it last week.
Right. Where EDG donate electron, EWG withdraw electron or take electron. So EDG on diene makes the Diels-Alder reaction faster. EWG on a dienophile makes Diels-Alder reaction faster. Right. So an EDG is anything with a lone pair or R group. EWG is anything that is uh double bonded or halogen X, like chlorine, bromine, or anything like that. Another way you could think about it is that EDG, the atom is always partial negative or full negative. Because if that atom has a lot of negative charge, it has a lot of electrons to donate. And EWG is always anything that is partial positive charge or fully positive charge, meaning that it wants to gain electrons, it wants to withdraw electrons. Does that make sense?
Yeah.
Yeah, right. So let's look at some examples of EDGs and EWGs. Let's say we have these dienes here. That R group is an EDG. This is an EDG because that oxygen there has two lone pairs of electrons and is partial negative. Another EDG could be an H2, which this nitrogen here is partial negative and has a lone pair of electrons. Um, Now let's look at some, oh, this one more EDG here. Let's say we have that, where this is an EDG because this oxygen here has lone pairs of electrons and it is partial negative. Now let's look at some EWGs. This right here is an EWG because this is the atom we focused at. We don't focus on this oxygen here because that oxygen is too far away. We look at the first atom attached to the dienophile, which is that carbon right there. That is partial positive charge. That's an EWG. And it's also double bonded. Another EWG you could see is this ester right here, which is different. This is different than this one because you notice how the first atom attached to the diene is that oxygen right there.
Yeah.
In this case, the first atom attached to this dienophile is that carbon right there, which does not have any lone pairs of electrons. It is partial positive with a double bond. So that's why that's an EWG. Another EWG that you could see is NO2, which looks like this, where the first atom attached to the dienophile is this nitrogen right here that is fully positive charge. And since it's fully positive charge, it is a strong EWG. It wants to get electrons as soon as possible, right? So that's the difference here. Like NO2 is an EWG, and H2 is an EDG because NH2 has a lone pair of electrons and partial negative charge, where NO2 has no lone pairs of electrons and a full positive charge, which is why it wants to withdraw electrons or get electrons,
Hmm.
right? And the EDG here has a lone pair of electrons which can donate electrons. Okay. So here's the residual selectivity. Let's say we have this diene right here, and we put that in OCH3. Um, when we draw the resonance structure of that EDG is gonna donate electrons into diene like that. Push this double bond down here, and that double bond pushes down there to get to this negative charge right here, and a positive charge right there. Right? If we have an EWG like this carbon here is partial positive, so it wants to gain electrons. It's going to gain it from the dienophile, push that double bond out to oxygen to get this resonance structure here. Right? Do these resonance structures make sense, or do you have any questions on these resonance structures?
So like dying are always EDG.
Diene will most likely always have EDG to make the reaction faster.
Okay.
Yes. Diene, EDG, dienophile, EWG.
Okay. And when you say dienophile, is it because it has um why is it called like that?
Yeah, it's called a dienophile because it mm, it loves dienes. Diene is two alkenes. Dienophile is a
Oh.
thing that loves dienes.
Oh, okay.
Yeah.
Okay.
Uh-huh. Right. Which loves to react with dienes like that. So when we draw the resonance structures, we see that these charges here are aligned because opposite charges attract. Negative charge here is attached to that positive charge. Negative charge here is attached to that positive charge. So now let's draw out the original form of the diene and the original form of the dienophile. We know that there's a partial negative charge here, partial positive charge here, right? I'm going to highlight the backbone of the diene, which is this part, and highlight the backbone of the dienophile, which is that part, right? Even though the positive charge was on that oxygen right there, that gives this carbon of the diene a partial positive charge. And even though the negative charge was on this oxygen right here, the partial negative charge is going to be on that carbon of the dienophile. We see that the charges align, so we could make the reaction go through like that, and that right there, forming the six-membered ring with the alkene. And let's number this 1, 2, 3, 4, 5, 6. That's 1, 2, 3, 4, 5, 6. You know how carbon 1 was an sp2 carbon and it became an sp3 carbon? There would be stereochemistry now where the OCH3 could be wedge or dash, and carbon 6, that group would have to be on the same side as that OCH3 group. This looks wrong because you know how there's a lot of steric hindrance going on, like they're on the same side, and that makes more steric hindrance, which is less stable. This is actually more favored because of the p orbital increase right here, because of something called the endo rule, which means that we want the groups to be on the same side, right? This is because if we draw in the diene, which is like that, with the OCH3 group, and a dienophile like this, we see that there are p orbitals here on the diene and dienophile, which those p orbitals can do resonance with each other if they are aligned, if they are right next to each other. And to make them right next to each other, we have to put them on the same side, right? So if they're on the same side, they have more resonance, which is the p orbital overlap, which makes it more stable. And this overpowers the steric hindrance factor, right? And I'll go over more like the whole complete guide for Diels-Alder for the next review session this week. Content review uh 9. Yeah, 9
Okay.
on Wednesday. Right. But here are just the basics of it. Where in my opinion, Diels-Alder is the hardest section of this um chapter with the homo lumo orbitals and stuff like that. Everything else is easier than this.
Is it
Yeah.
because you need to, it just gives a lot of stereochemistry?
Yeah, a lot of stereochemistry here. This was not the only stereochemistry that you could see because you could have like another group here or here, or you could have another group there, um, or here.
So would all of them be on the same side?
Not all of them, because if let's say the dienophile had another group here that is trans, right? Like let's say this is an R group, trans to this
Yeah.
group here,
Yeah.
that means that this would have to stay trans as well,
Oh, okay.
right? But if the R group was cis to that group, then it could be cis to that group for the dienophile, right? And I'll go over more of those examples on Wednesday.
Okay.
Yeah. Mhm.
Uh, just to make sure both of them were on the same side because they,
Mhm.
oh, what was it?
Yeah, they are on the same side because they increase resonance. You know how all of these orbitals here are p orbitals, like sp2, sp2, sp2 bonds, which makes a lot of p orbitals here. And you know how
Yeah.
sp2 orbitals, p orbitals, they want to be right next to each other, adjacent, parallel to each other? Because if we draw like this alkene right here, we know that that alkene carbon has two p orbitals like that, which are uh like pi bonded like that, right?
Yeah.
If we have like another pi bond nearby, that means that we have another set of p orbitals nearby here, which we can do resonance because these electrons can hop around these p orbitals. Because you know how the resonance structure of this, we could do that and do that. They're able to hop around because there's a network of sp2 atoms here.
Okay.
sp2, 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 sp2. If there's sp2, then that means we have p orbitals here, 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 and here, where they are able to hop around in between each other.
Okay.
And to do that, we have to make them on the same side to make them able to hop around like that and do more resonance. And that more resonance factor overpower the steric hindrance factor. Like this looks unstable because they're on the same side, but it's more stable because of the resonance.
Okay, got it.
Uh-huh. Yeah. I will see you on Wednesday. Yes, I
Okay.
think.
Yeah.
Yeah. Any other questions?
No,
Yeah. Or maybe tomorrow night too for office hours. Tomorrow night. Yeah,
maybe.
maybe.
I'll try to do like more practice problems.
Yeah, like Alkyne, conjugated diene addition with X2, HX, and stuff like that.
Yeah,
Yeah. Let's see.
try my best. Yeah.
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 I know you're like 2 weeks. There's 2 weeks left for the second
Yeah.
midterm. Yeah,
Yeah.
it's starting early. That's good.
Yeah,
Yeah.
because I have another midterm next week, so
Yeah, you want to get that the like get some stuff done early, right?
yeah, because I don't think like if I leave it to next week, I might just don't have time.
Yeah, I know, because you gotta focus on your midterm coming up that next week.
Yeah.
Yeah. Right. But you get some one-on-one time because like there's no one showing up, but
Yeah,
right before the midterm,
true.
that's when like a lot of people show up, like 10 people or something.
Yeah, that's good.
Yeah.
Thank you so much.
No problem. I'll
Have a
see
good
ya.
night.
You
Yeah,
too. Bye.
bye.